Okay, so I have a 15-minute max on these little videos, so I'm probably gonna have to do a couple for each of these sections. But right now we're gonna talk about multiple linear regression. So if you remember, we did a scatter plot of our data, and we showed the best fit line, the line that best represented the data, the model, and the way that regression does that is through that least squares estimate. So they calculate all these different lines, calculate the predicted values, and see the sum of squares error to see how different each of the predicted values are from the actual value. This is the same principle for multiple linear regression, but we're adding more explanatory variables. So if you remember, we had the x and the y coordinates for each of the points, and then we created the line that represented them. That was a two-dimensional x and a y relationship. We're adding moving beyond that, adding more variables, and it becomes three-dimensional if you add one more. So if you see here, we add that x squared to the plane. So we have the simple linear regression with the line associated with the relationship between x1 and y. Then we have the same type of relationship over here. How is x2 related to y? We're just adding these in together. So this is with two explanatory values, and we're always looking at how these affect the y variable. And just as we did the least squared estimate to find the best fit model with simple linear regression, we do the same thing with multiple. So each of these points, we see how far that point is from what is estimated by the model, which would be on this plane. We do a sum of squares error and see which of these models, whether it's tilted at this degree or whether it's more flat or more tilted, which of those models best describes what's happening with y in relation to x1 and x2. So that's kind of the general overview of multiple regression. The independent variables vary independently. They are things that move on their own, vary on their own, and then they in turn affect y. So y will vary in relation to x and y, x1 and x2. And that's what we're trying to determine, how they vary. We're describing how the outcome varies in response to how the input variables vary as well. And the reason we're starting to add things is because it's going to describe more of it. So when we have simple linear regression, we're just describing one potential thing that will affect the outcome. In the example I just gave, we looked at birth weight, and there's a lot of other things that affect it besides just the gestational age. The prenatal care that the mother is getting, many things are affecting that. So when we just look at the one variable, we're not getting a full picture that we can predict based on that. So we want to add variables in. At the same time, you're still going to be able to estimate the independent individual impact that each of the variables has on y, and I'll get to that. But you're sort of controlling or adjusting for the rest of it. So you can see how these things interact in relation to each other, so you can see if there's any interaction, confounding, and whatnot. So we'll get to that. The regression model, sorry that's a little blurry, but that's a y-hat. The regression model looks exactly the same as we had prior to this, but we're starting to add things in. So instead of having just one of these variables, we actually have two. We still have that beta naught, which means the y value when all of the x values are 0. So if I plug in 0 for both of these, I'm going to get my beta naught. It's also that point where the model crosses the y-axis. One thing to note before I move on, so we just added one more variable. So that's a 3D model. We're familiar with that. If we added another one, it would add another dimension to this. And if we added another and another, it'll keep adding dimensions to this. So just remember that the model has aspects of all of the input variables in it that create some sort of model that represents how y is going to vary, and then we can plug in our values into that model. So this plane looks complicated, but it quickly gets more complicated to the point where I can't even visually represent it on a computer. But that's just a side note. So we're adding in these multiple regression, multiple explanatory variables. So we can have 2, we can have 3, we can have, however many you'd like to have. So let's do an example. So let's pretend you're an aid group and you're delivering supplies, and you want to know, so you want to deliver supplies after some weather disaster. So maybe you work in Haiti and you're trying to deliver supplies effectively after the hurricane. So you want to estimate how long it's going to take to deliver those supplies, so you can make sure that you can plan ahead. So if we know how long it's going to take, we want to make sure that we can estimate that with a good model. So 2 of the things that you would put in there are total distance for the trip in miles, and then the number of stops that must be made during the trip. So if you have to stop to get gas a couple times, if you have to stop to get supplies, if you have to stop at multiple places. So you take a sample of 10 trips from maybe the last hurricane, and you want to record the total miles. So you call up these 10 people and say, how long did it take? How many miles did you go? And what are the numbers of stops? So I'd like you to pause for a second, and before going to the next one, I want you to list, you can do it verbally or on paper, list the dependent variables and the independent variables, including the units. So go ahead and pause that and do that. Okay, so the dependent variable is the travel distance. That's what we're concerned with, and that unit is miles. And then we have the number of stops, and that is just the frequency. It's a number. It doesn't have a unit in that sense. And then the travel time in hours. So those are our independent variables we're using to describe the dependent variable. Okay, so this is what your data is going to look like, and this is what your data will look like oftentimes. So you'll get, and I could have an ID here, an ID column with travel person 1, 2, 3 if I wanted to. But you're going to have a value for your independent variables and your dependent variables. So you're going to have a measure for each of a value for each of those measures. So there also another thing to think about is there's a lot of other things that could describe travel time. We could look at the weight of the load, the road conditions, the type of car. There's a lot of other things we could include in this model. The reason you don't do that is because every time you add a variable, it introduces error. So like we talked about with why we wouldn't do a bunch of t-tests and instead we just look at one ANOVA, we can avoid introducing that alpha error, which is that chance of saying something affects the travel time when it actually doesn't. We'll talk more about error in 2 weeks, but you want to avoid just what's called overfitting, and it's adding all these variables that are already encompassed within the variables that you're including. This is also called multicollinearity. So it's putting in a variable that is described elsewhere. So for example, I'm not going to include the gas used on the trip because that's going to be included in the travel time. So I'm going to use the same amount of gas based on the travel time. There's a SPSS tutorial on checking multicollinearity and assumptions of regression, and I suggest you do that, particularly if you're doing the final project and you get some counterintuitive examples. Oftentimes that's based on the fact that there's some multicollinearity. So again, that's just when there's there's multiple things included in the same variable. Speed of travel is going to be encompassed in the travel time. So we don't want to include both of them because we're introducing that error and we're diluting the model by adding that error. So we want to keep it to the most explanatory of the variables. If you look at this, the model is the same as the simple linear regression. We get our beta values for our population, and we have our epsilon, that error associated with our with the things we're not considering, and we have our beta naught values, and then we have our explanatory values, which could be however many you want to include in your model. So if you want to go ahead, we're actually going to do that analysis of that model, and it's distance traveled multilinear regression. So we go to Analyze, we go to Regression, and we go to Linear. So we're still looking at linear, and at this point we want to put our dependent variable in here. So if you remember, we're trying to see how travel time is affected by number of stops and total distance. So we're going to put travel time as our dependent, and then the remaining two in our independent. And one statistic that I'd like you to start incorporating is clicking on this confidence interval. By default, it will not be clicked. If you go to statistics and you add the confidence interval, it's going to give you confidence intervals for all of your beta values, which is going to be helpful. One more thing to note too, in this process, this is the enter value. The method tells you how you're incorporating the variables. We're going to use enter. There's other ways to look at this, but what enter does is it includes all of these values. If you want to look into these take into consideration how adding a variable will affect the model. So sometimes if you add in a variable, it's gonna make the error too much, so it's not worth adding it in. So it's comparing those two. So there's ways to compare the models within this method, but just for the purposes of this class, we're always going to use enter, so that's all of them going in. And you click OK, and then you get these values. So this again is what we saw with simple linear regression. We get our R-squared value. We get our, which our R-squared value is the same. The time travel is 92% of the variability in time travel, about 92%, 93%, is described by the number of stops and the travel distance. So that's a pretty good model. If I was writing up this data, I could say this is a good model. We don't have to look any further. 92% of it's explained here. So all we have to do when we're trying to predict how long the travel time is, we really can just look at these two variables, which are easier to estimate. I can estimate these from my desk. I don't have to worry about the topography of the land or anything like that. Then you get your ANOVA table, which again shows you the significance and the different errors associated with it. This is highly significant again. Significance of the overall model is highly significant. So number of stops and travel time are significant, a significant model when describing the travel time. And then we get our coefficients. So I'm going to stop there and then start a new video where we'll describe these particular coefficient values.